afternoon. We're going to get started. Today we have a visitor. I'm being observed and videotaped for a little bit, so you guys should all be on your best behavior. Here we have stacks for post-lab and pre-lab, so if you guys didn't already hand in your post-lab and pre-lab, please do so. Basically, I want to start by going through the experiments, and I'm going to talk a little bit about the pre-lab when we go through experiment 2. Did everyone feel comfortable with the pre-lab? Did everything go okay? Were there any questions about it? Calculating currents and voltages in the resistor network, and then also basically this potentiometer problem. Did anyone get the answer for the potentiometer problem? 15. That's right. That's exactly right. So if you guys got that, good job. If not, we will do the calculation just in a little bit. So basically today we're going to be... Oh, also I have everyone's homework, and I'm going to hand them out after we do this brief kind of intro. So I'll walk around and pass them out. Basically for the first experiment, if you guys looked in the lab handout, we're going to be using our resistor network from lab 1. And basically what we're going to be doing is using the DMM to look at the voltages and currents in that resistor network. And the reason we're doing this is so you guys can confirm that you did the calculations correctly in your pre-lab, and basically just get some practice using the DMM. So the first step is to measure some voltages. I just want you guys to remember that we're going to hook the DMM up in parallel with the resistor. And basically, you have to remember that based on the polarity that you hook up the DMM, you're going to measure either a positive or a negative voltage. So in the handout, it gives you a plus and a minus. And those pluses and minuses correspond to the red and black ports on your DMM. Alright, so that's the actual polarity reference that the DMM uses. If you hook it up in this direction, you're going to be measuring this voltage. But if you hook it up in the other direction, you'll be measuring the other one. So just keep that in mind and try and measure the one that's labeled in your lab handout. I think only 3 of them are labeled. 2 should be positive and 1 should be negative. So you guys can do that. And then basically we'll also be doing current measurements using the DMM. And again, we have this same issue of polarity. And also I want to remind you that we're going to be measuring in series, right? Because we have low resistivity between these ports and high between here. So you need to have your circuit and break your circuit, right? Break your circuit and then put the DMM right where you broke your circuit. So you can connect it to one end of the resistor, and then you can use a wire to connect it back into your breadboard or something like that. And again, depending on the polarity at which you make the connections, you'll read either a positive or negative current. And the convention is that the arrow should be your negative. Wait, no. Did I draw this correctly? Yeah. So basically the arrow, the tip of the arrow, you should be hooking up the red port on your DMM. So this is a positive current. Currents that we draw in circuit schematics are positive, and the convention here is that this will be a positive current. I think I lost all my markers. Oh, here they are. So current flowing in this direction is positive. And I just also remind you guys that positive current always flows from a high potential to a low potential, so you keep that in mind too. Any questions about the first experiment? You guys should be able to do that one pretty quickly. Also, I want to mention that this lab, there's some pretty tight time constraints. So you want to try and move quickly through experiment 1, and then pretty quick through experiment 2, and then leave a lot of time for experiment 3 because it's going to be a little bit complicated. So for experiment 2, we're now introducing the potentiometer. We're going to use a 10-volt supply, not a 6-volt from experiment 1 is 6-volt supply. So remember that. And basically we're going to be hooking up the potentiometer and looking at how the potentiometer works as we change the face dial. And basically how it works is that it has 3 terminals, and between A and C right here, there's always a 20 kilo ohm resistance. But between this 3rd terminal, we can vary the resistance by just making contact here when the dial's turned one way, and here when the dial is turned the other way. So let's say if the dial's turned here, then the resistance between these two ports is very small. But when I turn the dial up here, the resistance increases between those two. So basically, you can vary the resistance between those two or these two terminals by turning that dial. But the resistance between these two is always fixed, and it should be 20 kiloohms. So in the pre-lab, you guys were supposed to calculate two resistors you could use with the potentiometer in order to change this 10-volt swing. If I hook this 10-volt supply up to just the potentiometer itself, and I turned it from one maximum position to the other one, I would get a voltage here of 10 to 0. Does that make sense to everyone? So now if I put a resistance here, call it R1, and a resistance here called R2, what would you guys expect to happen? If I just put a resistance on top, what would you guys expect to happen?
Well, if you put the plot all the way down, it would be 0.
It would still be 0, right? But then what if I put it all the way to the top?
You would get the resistance of the plot, or you would gain some voltage.
Would I get 10 volts, or would I get more or less?
You get less.
That's right. And why? Because voltage division, basically. So that's right. So now, what if I put a resistor here, but left this one short-circuited? Anyone have the answer?
You have it at high, it would be 10 volts, and then at low, it would be less than 10 volts.
Exactly. So what you guys were supposed to do in the pre-lab is pick two values that would make the swing go from 7 to 3 volts. And the way you do this, basically, is just through voltage division. And how we do that is we just write the formula. So when the potentiometer is all the way in one direction, we should get 7 volts. So I'll say it should be, I'll just write 7 here for 7 volts should be equal to our voltage supplied times, if the potentiometer is all the way turned on, the resistance would be the R potentiometer plus this R, which I'm going to say R2, and this R. That's a really bad 2. And we would divide by the total resistance in that circuit, right? Since it's voltage division, we would be the voltage across these two resistors divided by, or this resistance divided by the total resistance, which is just this formula, right? So this V supply is just 10, so then I'm just going to move the 10 over. So 7/10 should be the ratio of these resistance to these. Does that make sense? I think it should make sense, right? Does it make sense to you guys? So then the other one would just be 3/10 is equal to R2 over the same thing. So now you see that the denominators are the same. Basically, if I do some whatever algebra where I forget what it's called, where you like multiply the top and the bottom and do all that neat trick. Basically, I can say that this denominator is equal to 10/7 times R potential plus or potentiometer, which is also equal to 10/3 of R2. So, can you guys read any of this? So then I can just ignore this. Now I have a single equation of just one unknown, and I can get rid of the 10s, and then I can solve for R2. And basically you should get 15 kiloohms. And then, if you think about it, actually you can stop there, because the swing was originally 10 to 0 volts, and now we want it 7 to 3. So that's actually symmetric about the midway point. You're taking 3 off the top and 3 off the bottom. So actually you know that R2 and R1 have to be equal. So they're both 15 kiloohms. So that's the second experiment. Are you guys have any questions about that? Yes?
The other resistors here,
No, you'll have to get them in the stock. And you also need to get some in the stock room for experiment 3.
Are they?
And if you don't have
do we have enough of the 15K, or is
probably no one had any problems last section lab. Yeah, until you guys are the very last lab, so. Okay, so the third experiment is the hardest one, and I know that I talked to you guys last week about this 50 ohm terminator and the 50 ohm setting in the function generator versus the high Z. Basically, we're going to be looking at that today, but we're going to be looking at it in terms of the loading effect. So did anyone read the lab handout, and can anyone tell me what the loading effect is?
When you have like small resistance in your circuit, you'll pull a large current, which, depending on your voltage source, if it has an internal resistance, like most real sources, it'll drop the voltage of that source.
It will drop the voltage what?
Of the source. So like a battery has an internal resistance, that's the same thing.
Yeah.
So like if you're pulling a large current through your circuit, it'll actually lower the voltage
Which voltage?
of the source. Supply.
Okay. I mean, you're right, except usually we refer to it as the load voltage.
Okay.
So the one across your load is going to be reduced.
Okay.
The supply voltage, we're just going to assume, is idealized and fixed.
Okay.
But yes, that's exactly right. And the reason it does that is because of voltage division. As you said, there's some internal resistance here, and that's why we're doing experiment 3 and experiment 2 together, because this is basically just voltage division. And the loading effect is basically just voltage division. So you have a practical supply, just like he said, and it's going to have some source voltage, 5 volts, but it also has some internal resistance, which we call RS. And when you have a load resistance here, if it gets really, really small, that supply resistance is going to begin to dominate, and some of the voltage is going to drop across here, and your load voltage is going to decrease. And actually that means that your load current starts increasing too. So, I mean, actually your load current should increase, because as you decrease the resistance. Anyway, so what you guys are going to do is you're going to use the high Z setting, and you're going to source a 5 volts sine wave, and you're going to measure